Hi everyone, this is Anushka and welcome back to my channel in Economist. So in the previous day, we have started off with our discussion of panel data. And if you have followed my previous lecture, there I have discussed what is panel data in general, what is the concept. And then we have also discussed what are the different types of panel data possible. That is, we have gone into the balanced panel and the unbalanced panel, and then we have done a comparative analysis between the two. Right, so we have stopped at this place in the previous video. If you haven't watched that video, that is the first video on panel data. Please check those videos out. I will give the link in the description. You can find it there. Now, from today, we will go into the estimation process of the panel data, right? So this is very important. How do you estimate panel data? We will study this, and it will take many videos. I'll make subsequent videos and I'll explain each of the methods in details, right? So let us start with the discussion today. So for that, I have taken a context. This is a specific context that we will use to model our, panel data, right? See here, suppose we have four different forms, right? In the previous video, I have explained in panel data, you have different entities and you will have different time points. So here, the four different forms will mean four different entities, right? Individual entities, or they are the cross-sectional units. Let me write it down. They are the cross-sectional. They are basically the cross-sectional units that you will have. And now you will observe the production, basically the production of four different forms. You will observe it for 20 different years. So this 20 will be the number of time series units, basically. The time series units. And if you remember, we have discussed that panel data is basically a combination of time series and cross-sectional data. So here we have cross-sectional units. There are four cross-sectional units. See here, I have written I is A, B, C, D. So A, B, C, D are these four different forms that we are talking about. And you have 20 different periods. So that will be denoted by small t. Cross-sectional units are denoted as small I in general in panel data analysis, and time period is usually denoted as small t. Here I have taken some specific years from 1980 to 1999. These are 20 years altogether. So we want to know what will be this scenario. So basically here the table will look something like this. Here we will have all the years 1980, 1981, 1982, all the way up to 1999. Here you will measure the years, and here you will have the four different forms. Here you have A, here you have B, here you have C, and here you have D. And here for every cell, you will have some values, right? Some numerical values of production will be there, and this is how the table will look like, right? This is the panel data that we are talking about. Now, can you pause the video and think how many total number of data points you will have here? How many total number of data points? You have four different forms, A, B, C, D, four different forms, and you have 20 different years. So how many total data points you will have? You will have 80 total data points, 80 total observations. So for every cell, you will have one data point, right? So if I draw this, so if you draw all these cells, right, all the way here, here it will be some discontinuity. All the cells, if you draw, 1, 2, 3, 4, 4 columns will be here. So here, this is the first cell. You will have some value here. Here you will have some value. Here you will have some value. Here you will have some value. So here for the first cell, you will have four values. For the second cell, you will again have four values. So altogether, you have 20 different rows. And in every row, you will have four values. So basically 80 observations altogether, right? So that is how we have got the total number of observations that we will work with. That is 80 total number of observations, and we have denoted this total number of observations by capital A. Now, the question here is, how do you model this scenario and estimate it, right? How do you estimate? So this is a classic panel data scenario where you can see four cross-sectional units and 20 time points. So this is a classic panel data. This is a classic panel data. In the previous video also, I have shown you a table like this. Again, I'm saying if you haven't watched that video, please check that out. That was the introductory session. And in this video, I'm just building upon it, right? So please check that out. You will understand. So this is a classic panel data scenario. Now the question is, how do you model this scenario and how do you estimate it? Now for that, you have different process, namely you have 5 different methods in which you can do this. See here, this is a very, very important thing, right? I know many students, struggle in this. That is why I clearly wrote everything out previously so that you find it easier to understand, right? So estimation in panel data can happen in multiple ways, and I have written all the 5 possible ways. Now, the first assumption here would be the general assumption for all these methods. General assumption for all these methods will be all the explanatory variables that you will use. X, basically X is the explanatory variable that will be non-stochastic in nature. Non-stochastic, I hope by this time you know what is non-stochastic. I have made separate playlist on econometric method and advanced econometrics. This is the playlist that is going on. And in both the playlists, I have used this non-stochastic term multiple times, right? It basically means that X does not have any probability distribution. In repeated sampling, it will take fixed values. That is what is non-stochastic. So X is non-stochastic. This is the first assumption. And the second assumption, which is general for all these 5 methods, will be this, that the error term, or namely the idiosyncratic error term. This also I have introduced in the previous model, that I have said in general panel data will have 2 different kind of errors, but here I'm just generalizing it. We will see how this will vary in different scenarios, in different methods. So in general, the idiosyncratic error term, which varies with time, also with observations, this is a random stochastic term. It will follow a normal distribution with mean 0, variance sigma square for all I and t. So these are the 2 general assumptions that we have to make that will be applied for all these 5 different methods. Now let's look at all these 5 different methods. The first method, so today's video will be on this first method. I'll explain how do you model the panel data, the context that we defined earlier using the first method. And then we will go into the advantages, disadvantages, and the coding of this particular method, right? So this is the agenda for today's video. So see, in method 1, what you assume is that the intercept of the model and the slope coefficients are all constants, both across time and across space. So this is the first assumption that you have to make in order to model this panel data context that we have defined. So basically, we will try to define this. We will try to model this context. Now, if you use the first method, you will assume both your intercept and your slope coefficient. They will be all constants. Now, if they are constant, we will say that it will not particularly explain the nature of the panel data. So if you have seen the previous video, there I have explained the basic aim of panel data, the basic usage of panel data is to control for individual specific heterogeneity, right? I have explained this terminology, individual specific heterogeneity. Now, if you assume that all your intercept and your slope coefficients are literally constant, then you cannot explain that heterogeneity, that individual specific heterogeneity. And that will be a major drawback for this particular method. Now, firstly, let us see how do we do that. I'll come to each of them. Okay, let me first, you can take a look at all the different methods. Method 2, that all these methods we will discuss in the successive videos. Basically, in method 2, we assume that the slopes are constant, but the intercept varies over individual entities. I'm not going into details in this video. I'll cover them, each of them, in the next videos. In method 3, we assume that the slopes are constant, but the intercept varies over time and individual entities. In method 4, we assume all the coefficients vary over individual entities. And in method 5, we assume all coefficients vary over time and individual entities. So basically, all these are different methods based on the nature of the slopes and the nature of the intercept coefficients. Slope coefficient and the intercept coefficient, the nature of them will determine the model nature. The specification of the model will be done depending on the intercept and the slope coefficient. Now let us firstly focus on the method 1. Method 1 is the base model, right? Method 1 is the base model which will help us to go into more advanced modeling. And now let us see how do you actually do this. So we'll start with method 1, where we assume both the intercept and the slope coefficients are constant. So what will be the model here? The model will look like this. YIT, right? YIT, here you will have 2 suffix. One is for the cross-sectional unit, which is denoted as this I, and one is for the time period, which is denoted as the T. So YIT can be written as beta 1 plus beta 2 X2IT plus beta 3 X3IT plus the idiosyncratic error term, which is UIT for all I and T, where this beta 1, beta 2, and beta 3, they are all constants. So this is our basic assumption. So beta 1 here is what? Beta 1 here is what? Is the intercept coefficient. See, the intercept coefficient that has to be constant across time and space. So beta 1, it does not have anything like this. Beta 1 IT. There is no suffix like I and T. This is not like this also, and this is not like this also, right? So no other, only one is there. See, no I and T is present. That is why it is a constant. If I and T is present here, it will vary with, that will mean that it will vary with I and T. But here no such suffix are there. That is why the intercept term is completely constant across time and space, which is our assumption in this model. Also the slope coefficients, beta 2 and beta 3, these are the two slope coefficients. They are also constant across time and space. Across time and space, not varying with entities, not varying with time. That is the method 1 of estimating the model. Now, if you have a model like this, so this is what our model looks like, right? This is what our model looks like. And if you have the model like this, then what you are doing, you are essentially avoiding any of the panel data structure. You are considering it as a cross-sectional data. Now, how do you estimate this? How do you estimate this model? This model can be estimated using simple OLS regression. Simple OLS method can be used to estimate this, because see, it is just like usual regression model that we have done so. Right? There is no difference, because this UIT, this idiosyncratic error term, will follow normal distribution. This we have written earlier. This is there. And we will also assume that this explanatory variables are not correlated with the error term, idiosyncratic error term. That is also there. So there is no problem of endogeneity. Also, in usual regression, we have seen that these coefficients are all constant. Basically, they are fixed for a particular model, right? So this is a simple this is a model which can be estimated using simple OLS regression, ordinary least square regression. That is why this method is known as the pooled regression model. Pooled regression, right? This model is known as the pooled regression model, which can be simply estimated using ordinary least square method. I hope this is absolutely clear. And if you estimate this, what is the end result that you will get? You will get the value of y as the estimated value of beta 1 cap, the estimated value of beta 2 cap x2 it, or let me write x2, doesn't matter, and beta 3 cap x3. So this will be the estimated model that you will get from here. So it is known as the pooled regression, because you are pooling together both the cross-sectional units and the time points, and you are combining it, you are treating it as a cross-sectional unit altogether. Right? It is no longer, if you model in this particular fashion, it is no longer a panel data. Please understand this, why it is not a panel model. It is not a good way of modeling the panel data, because you are ignoring all the features of the panel data. The main feature of the panel data is that you can individually find out the entity specific variations or entity specific heterogeneity, which you cannot do, because this coefficient, these coefficients are not useful at all, right? These coefficients are not useful at all. They are not varying across time points and across cross-sectional units. That is why no heterogeneity, no individual heterogeneity can be found out, and hence no individual heterogeneity can be controlled for. So that is why it is a very oversimplified model, and it is a base model which basically builds the foundation of the estimation process of the panel data, and which will help us to further formulate other better models, and then we can also do the comparative studies. Now understand a few things, few important things about this kind of modeling. If you use this kind of modeling, see here, the first point is what I have just told you, that pooled OLS. This is known as the pooled regression model or pooled OLS model, ordinary least square. It treats the panel data as if it were pure cross-sectional data. Right? This is what I explained you just now. This is very important. It does not, it does not ensure the panel structure of the model. See, if it were pure cross-sectional data, ignoring the panel structure, meaning it does not account for individual or the time-specific heterogeneity. So it is basically ignoring the main essence of the panel data structure. It does not take into account any individual specific. Individual means entities. Basically, it can be firms, it can be countries, it can be people. In our context, it is firms. The four different firms that we are talking about. And also, it is not taking into account the time specific heterogeneity. So this is one of the special features of this model. Now, what are the basic assumptions of this model? First is no individual specific effects, as I've told you. So it is usually denoted as alpha I, right? Alpha I denotes the individual. Individual is I basically. In our example, I is ABCD, simply the four forms that we are considering. So it assumes that there is no individual specific effect. So every form is basically unique and the individual form effects cannot be obtained from the model itself. So if you want to obtain that, you have to add another term like alpha I in the model, which we are not considering. If you consider it separately, then this problem can be solved. This feature can be captured then only, but in our simplified model, it cannot be done. The second point is that there is no time specific effects, which is denoted as lambda t. These are basically the usual notations that we use. In panel data context, we use this notation. These are the standard notations that we use. So alpha I is absolutely zero. Alpha t is also zero. If the effects are present in the model, then this will be not equals to zero, and lambda t will also be not equals to zero, which is not our case here. So they are simply zero. And the third thing, we assume that the error term, that is the idiosyncratic error, is uncorrelated with the explanatory variables, which helps you to understand the explanatory variables are exogenous in nature. There is no problem of endogeneity in our model. And this is the note one. These are the first observations that you can do of this particular model. Now, the second thing is that when do you use this model? Why do you use this model and when do you use this model? The usage is the unobserved individual characteristics do not matter or are uncorrelated with the regressor. So this is the first use case. When do you use it? When you see that the unobserved individual characteristics, they do not matter. Even if some special, so in the previous video, I've given you this example that if you are taking factory workers, then innate ability, their inherent ability will be one such individual specific characteristics. Now, if you feel that characteristic is not strong enough to affect the dependent variable, that is the wage. In the previous example, I am giving you the example of wage. If that innate ability, you understand, you assume that it will not affect the outcome variable, then you can simply ignore it. So this is one of the use case when you can use this oversimplified pooled regression model to estimate your penalty. Or your, the unobserved individual characteristics are simply uncorrelated with the regressor. The second is you do not expect any sort of heterogeneity across individuals over time. You assume that all the factories are absolutely same. Every production process is absolutely same. There is no special feature in any of the firm. So there is no possibility of any heterogeneity if you assume that. If you expect this kind of a thing that no individual, you know, variations is possible, then also you can use this kind of oversimplified model. And the third thing is the most important. It is used as a baseline model. This is also what I was talking about. This is a baseline model used for comparison for more advanced estimators like fixed effect and random effect. That these are also important things that we will discuss in the subsequent videos. In this video, I'll explain only model one, right? So I'll talk about this fixed effect, random effect in some other videos, subsequent videos. So this is basically an oversimplified baseline model, which helps you to compare it with the more advanced estimation process, right? So this is note number two. Now let's move on to see what could be the possible disadvantages of this kind of modeling. There are different disadvantages, as I have explained to you. First is omitted variable bias. It says if there are unobserved time invariant individual effects. So we have assumed that alpha is equals to zero. But what if alpha is not equals to 0, which is more realistic? All the individual units cannot be the same. Every individual will have some kind of specific abilities which might affect your model, which might affect the individual outcome or the outcome variable that we are interested in. So it is not always true that alpha I will be exactly equals to 0 for all I, which is our assumption in this model. So if this is the case, if alpha I is not equals to, it happens to be not equals to 0, and this effects gets correlated with xit, that is the explanatory variables which are present in our model, then the estimates will be biased and inconsistent. So basically the covariance of xit and alpha I, if this thing becomes not equals to 0, we are assuming that alpha I is present, alpha I is not equals to 0, it is non-zero, it has effect on the outcome variable, and also it gets correlated with the explanatory variable. In that case, there will be severe problems. The estimators will be biased and inconsistent in nature, which is the first problem of using this oversimplified model. Now, the second thing what can happen is that it ignores the correlation of the observation within individuals. This is also an important point, which is the difference from the fixed effect model. Basically, within individual, differences are also not observed. So we have four different forms here, A, B, C, D. What happens if the production of form A gets correlated with the production of form B? So there are multiple data points in A and B over different, across different time points. So what happens if two forms get correlated? A, B gets correlated or B, C gets correlated. So this within individual means entities here. In our context, it is the different forms that we are taking into account. So if different forms, if the data points within the forms get correlated, then it will lead to underestimation of the standard error, which is also one of the major drawbacks, right? It is also very seen. This is a very, valid problem, which is often seen in the panel data. If you're a researcher, you might have encountered this in your panel data. So it's very important. And the third thing that can happen is that here we are assuming constant variance and no autocorrelation, but it also rarely holds in panel data. In panel data, this homoscedasticity assumption, that is, we have assumed that the idiosyncratic error follows normal distribution with mean zero and variance sigma square. So this homoscedastic variance is not often seen. Also, non-autocorrelation, this is also another assumption. That is, so all the basically classical linear regression assumption hold. That is why we can use OLS in the first. So to apply OLS, all the classical linear regression model assumptions must hold. And this is a very rigid assumption because in general, in real life, in case of panel data, these assumptions rarely holds. So this homoscedasticity and independence assumptions often get violated, which is also one of the problems. So these are the dips. So this is basically a flawed model, as you can understand very well. It cannot capture the true essence of the panel data. This is just a baseline model on which we will build up new advanced estimation models, right? This is just a simplification of the models. Now, what are the advantages? There are few advantages of this model. First is that it is very simple and computationally fast, right? Here you can see the example. I have written the Stata code. So if you in Stata, if you import the data set and just write one line of a code, your entire pooled regression will be executed. So Stata code is just one line. You have to just import the data set. I'll make a separate playlist on everything, every econometrics topic that I have covered so far. I'll make a separate playlist on that. That I will do this hands-on with you, and we'll see how to do this thing. So I'll make a separate playlist there. I'll explain that more. But see here only this much data code is needed to pull off this pooled regression, pooled OLS regression. Here first write REG regression, and then write the outcome variable or the dependent variable, and then write all the independent variables. Only this much if you write, entire pooled regression will be executed. Here Stata will assume that you are pooling the data, ignoring the panel structure. No panel essence will be there, only pooled OLS will be executed. So it is simple and computationally very fast. If you want to know the just general overview of the model, you can run this regression in Stata. Second thing is that it is for benchmarking of other models. So you'll basically compare this pooled OLS. This is the basically benchmark. You will compare the fixed effect models, random effect models with this pooled regression model that we will do in our subsequent videos. So this is one of the advantages. And third thing is that it can be used when the variation across units and time are minimal or irrelevant. If you assume that there is no effect, no individual specific effect or no time specific effect, then you can execute this simplified model, right? These are few assumptions that I wanted to explain to you. Now here I have attached the Python code also. In Python stats model also you can perform this. Here is the code block. If you want, you can pause the video and take a screenshot. Here we will use the stats model. Stats model you will use, and you will write all the data points in the data frame. DF is the data frame which you can see here. Again, I'll do the hands-on in some other videos, so I'm not going into this. And this is the way you will explain. You will firstly run the code block. You will find out the output table, and you will get the summary table as your output, right? So this is the Python code block. You can do this in Stata, Python, or in RS, right? So the final thing, this is all basically I wanted to share with you. Now the summary table I have given. So what are the basic features of the pooled OLS in one glance? One glance, if you want to understand the entire thing, you can see this chart. That feature, what are the different features? Does your pooled OLS model controls for heterogeneity? We have seen no. It's a big no. Since all the slope coefficients and the intercept coefficients are just constant, they are not varying with individual entities, they are not varying with time. So that is why no heterogeneity can be found out. So if you can only do the controls if you can identify the heterogeneity, right? In this model, you can't even find out the heterogeneity. So how will you control it? This is not possible. That is why it's a big no. The second thing is time invariant regressor. Yes, even if you attach the time, it will not impact. Basically, they are all time invariant because everything depends on the slope coefficients and the intercept coefficients. So they are unable to capture the true essence of the panel data. So even if you attach the time component in your regressors, that will not matter. So so essentially they are also time invariant. So even if you attach the subscript, it will not matter. So this is true. Basically, time invariant is true. Now the third thing is that easy to implement. Yes, we have seen in Stata in one line only one code block will help you to and pull off this entire thing. So it is simple to compute. It is just the normal OLS in Stata and R or Python, any software you use, you have to simply write a small code block that will execute it. So it's very computationally, it's very fast. Fourth thing is that robust to endogeneity. The answer is no, because we have ignored everything. We have ignored the possibility of endogeneity here. We don't know if endogeneity appears, what will be the effect on this model. It will vary from situations to situations. So basically, it is not robust to endogeneity. We have assumed exogeneity here. We have ignored that endogeneity is possible in the model. We have completely ignored that scenario. And the fifth feature is preferred when. It is preferred when no observed individual or time effects is there, right? So this is all about the first method of estimation of panel data. This is the simplified base model, absolutely the foundation of estimation of panel data that we have covered in this video. In the next video, I'll go into method 2 where we see if we assume that the slopes are constant, but the intercept varies over individual entities, what will be the effects? And we will do the similar analysis. We will see the model structure and we will see all the advantages, disadvantages, special features, and all the summary, right? So this is the agenda for the next video. I hope you like this video. Let me quickly summarize. Let me take you through once what we have done today and then we will stop. So firstly, we have defined the context in which we are doing all the estimation. You should have a panel data with you before going into the estimation. Now I have told you that there are 5 different kind of methods that you can apply to estimate your panel data. In this particular video, I have focused on method 1 and I have shown you how you can work with that. So in method 1, this is the general structure of the model. You can simply apply the OLS regression because it satisfies all the classical linear regression model assumptions. Even though we have used the panel data, it is unable to capture any essence of it since it is an oversimplified base model. So this can be simply estimated using the OLS method. That is the ordinary least square method. That is why it is also known as the pooled OLS regression. Pooled OLS regression model. The method 1 is also known as this. Now we have seen some of the basic features, some of the model assumptions, and when to use the model, what are the different disadvantages, what are the different advantages. And then we have also seen how to code this thing. This is also the subject matter for some other, right? So thank you so much today for listening me out. I hope you like this video. If you do, please give me a like and do subscribe to this channel in Economist, because that will help me to grow my channel and that will also help me to make such useful videos for you every single week. I'm trying to post 3 to 4 videos every single week, and it takes a lot of time and effort from my end. So if you like this content and this is adding value in your life, you understand things better through my lectures, then please support my channel. Do like, hit the like button and do subscribe to this channel in Economist. And I'll keep on making such useful videos for you in the coming minutes, right? So thank you so much for your time and let's meet you in the next.